Hey everybody! For the next two mini lectures, we are going to talk about cosmology. And I think that the video I had you all watch for the discussion is like one of the best videos I've ever come across to explain cosmology. But I'm going to do a little bit more of explaining here in the next few mini lectures. There are a lot of things that go into cosmology. Cosmology is the study of the structure and evolution of our universe as a whole. And cosmology tries to answer these primary questions. How big is the universe? What is its shape? How old is it? How did it form? And what will happen in the future with our universe? Now, there's a lot of things, again, in here. A lot of cosmology might feel a little bit philosophical because there's a lot of things we don't yet know about our universe. And you'll see that when we talk about the Big Bang, we don't really know what happened prior to the first 10 to the minus 43 seconds of our universe. What we do know today, though, is plenty of things from observations. We know that our universe is expanding, and it's filled with a very low energy background radiation called the cosmic microwave background. The radiation and expansion of our universe imply the universe began about 13.7 to 13.8 billion years ago. And our universe began as a hot, dense, violent burst of energy and matter that we call the Big Bang. Now here's something called the Cosmological Principle, which you've already seen before in a previous reading quiz, and it kind of tied into what we're talking about with other galaxies as well, when we're thinking about what's happening in other galaxies beyond our own. But the Cosmological Principle essentially says that whatever happens in our little corner of the universe must be happening in all other corners of the universe too. That the laws of physics that apply here are the same as the laws of physics that apply in any other galaxy, any other solar system. Okay, we can apply Kepler's laws to the planets in our solar system. We can apply them to any other planet in any other solar system, in any other galaxy as well. Okay, the Cosmological Principle, you know, in its true definition, says that there's a lack of preferred direction in the universe. We assume that our universe is homogeneous and isotropic. Homogeneous means it's the same everywhere. Isotropic means that in whatever direction you look, it's going to be the same. So the universe will look the same to someone no matter where they are located. They could be located here on Earth. They could be located on another planet on the other side of our galaxy. They could be located in another galaxy many billions of light years away. But no matter where they are, the rules of physics must hold. Without this assumption, there's no way that we could proceed in physics. We're just going to hold the universe to the fact that physics is the same no matter where we are. So I want to think about something called Olber's paradox. It has to do with early theories of our universe. So Isaac Newton thought that the universe was infinitely old, infinitely big, and unchanging. In 1823, Heinrich Olbers offered what we call Olber's paradox. If the universe extends forever and has existed forever, the night sky should be as bright as day. Olber reasoned that, you know, if our universe is infinitely old and infinitely big and unchanging, that no matter which direction you looked in the sky, you should see a light from a star. Our entire sky should be lit up by stars within our galaxy and stars within all the other billions of galaxies in our universe. But we know that that's not the case. We can only see with our naked eye a few thousand stars in the sky on any given night. Well, the universe has a speed limit, and things cannot travel faster than a certain speed limit. The finite age and speed of light means only a finite volume of starlight is available. So therefore, most of the night sky is dark and we see only a few pinpricks of light. The age of our universe limits the distances we can see since the speed of light is finite. So from our point here on Earth, the distance that we can see, the furthest thing we can see out in our universe, is directly determined from the age of our universe and the speed of light. So the maximum distance that we can see is called the cosmic horizon, okay? So in a static universe, assuming that the universe is not expanding, the distance in light years to the horizon, the furthest things we can see in our universe, equals the age of our universe. Okay? If something is a distance away from us in a light year, it takes light that many years to get to us from that distance, okay? So we know that there are galaxies that exist beyond this cosmic horizon, but their light has not had time to reach us yet. So that's the important thing, okay? So the thing is, we are only able to see a portion of our universe. There are galaxies that exist beyond what we can see right now with telescopes. In the early years of the 20th century, astronomers imagined the universe as a static place with only the Milky Way and a few companion galaxies. And it wasn't until the 1920s that astronomers realized the universe was filled with other galaxies millions of light years apart, and that the universe was expanding. So there were two ideas. Either the Milky Way was alone in our universe, or the Milky Way was only one of others in our universe. And we've since learned that with more observations, we are only one of the many, many galaxies in our universe. And no matter which way you look in our universe, you see about the same number of galaxies. But these galaxies are not spread out smoothly in our universe. They're spread out into clumps or groups. Now, here is a simulation of galaxy formation. It's a computer simulation using many, many hundreds or thousands of parallel supercomputers. And it is also showing lots of galaxy cluster formation are these red regions here. And along these green filaments is also where you're finding a lot of galaxy formation. So even within these computer simulations, we're replicating what we're able to observe in the universe, and that is that galaxies prefer to form along these filaments, kind of a web-like cellular structure within our universe, and there are voids in between those filaments where less galaxies are found. We talked also about how these galaxies obey Hubble's law. The speed at which these galaxies are receding away from us is proportional to their distance away from us. And this proportionality is given by the Hubble constant. So this motion away from us is due to, we said it means that our universe is expanding. It's due to the expansion of space itself. It's not like bomb fragments going off through the air, but imagine it's more like you take a balloon and you glue buttons onto that balloon and you blow up the balloon. Those galaxies are going to be receding away from each other as that balloon expands. If we take what we see with the universe's expansion and we play it backwards in time, that implies that all mass must converge. If we take our simulation of our universe and run it backward in time, if everything is expanding now, if we press the rewind button, everything is going to converge back to a singular point. So running our universe's expansion backwards implies that all mass becomes confined into a very small volume that here in the slide I'm calling the primeval atom, but in the Crash Course Astronomy video you watched, I think Phil referred to it as the cosmic egg, but that's sort of the seed of material from which our universe formed, okay? So another question that astronomers in the past have pondered is, are we at the center of the universe, or what's at the center of the universe? The recession of distant galaxies often leads to the misconception that the Milky Way is at the center of the universe, because in any direction that we look, we see that the galaxies are moving away. are receding away at a constant speed. Everything is receding away from everything else at the same speed. Because space is expanding, no matter where you are located, galaxies will always move away from you. There's no preferred center to our universe. Okay, so that's a really important piece of information. There's no really anywhere where we can call the center of our universe. All parts of the universe are expanding away from each other at the same speeds, and we can really identify no place where we can say, hey, that's the center. For example, here we've got a whole bunch of galaxies, and here we are in the Milky Way. We're in the Milky Way. The Milky Way is not receding away from us because we are in it. So the recession velocity of our galaxy is 0. But if we look 10 megaparsecs in one direction or 10 megaparsecs in another direction, we see all the galaxies away from us at 10 megaparsecs are receding away from us with the same speed of 700 kilometers per second. If we go twice the distance away from our Milky Way in either direction, 20 megaparsecs, that galaxy is going to be moving away from us, all those galaxies at 20 megaparsecs. The further away from us, the faster they're going to be receding away from us. So those galaxies out there are receding away from us at 1400 or 1400 kilometers per second. And then we look at another set of galaxies that are 30 megaparsecs away from us. They're going to be receding away from us at 7 times 3 times the distance of this galaxy at 10 megaparsecs. So that one's going to be receding away from us at a speed of 2,100 kilometers per second. Okay, so now, we were 30 megaparsecs away. Alien galaxies receding away from us at 2,100 kilometers per second. Now let's imagine what these recession velocities look like as seen from this alien's galaxy. So from this alien galaxy, they are in that galaxy, their galaxy is not receding away from them. But if they look out at 10 megaparsecs away from their galaxy, all those galaxies that they see at that distance are going to be moving away from them at 70 kilometers per second, or 700 kilometers per second. If they look out at 20 megaparsecs, all those galaxies will be receding away at 1,400 kilometers per second. Then if they look away at 30 megaparsecs, all of those galaxies will be receding away from them at 2,100 kilometers per second. So no matter where you are in the universe, no matter where you look, if something is the same distance away from you in your galaxy as it is from somebody else in another galaxy, then all those galaxies will be receding away from each other at the same speed. Okay, so it doesn't depend on which galaxy you're in. That all boils down to the fact that there's no preferred center of our galaxy. Here's another way to think about the expansion of the universe. Imagine that we have a balloon and we draw some dots on the balloon, and we even draw a little wave pattern to represent a wavelength on the balloon. So we blow up the balloon. As our balloon surface expands, this wave of light on the surface of that balloon is going to stretch. And that means that as we blow up the surface of the balloon, that wavelength of light is going to expand. Remember that the wavelength of light was the distance between consecutive peaks or troughs in the wave. Okay, so if this light wave is traveling along through the universe, but our universe is expanding, that means that as the universe expands, that wavelength of light is going to be stretched. It's going to get longer and longer and longer. Okay, and so we call that a redshift. Remember, on our visible part of the electromagnetic spectrum, light with longer wavelengths is red. Light with shorter wavelengths is blue. So anything that has an expanded wavelength, we say, is redshifted. That's why we say that the light from galaxies further away from us is redshifted, because of this expansion of the universe, expansion of the light that we see from those galaxies toward the redder end of the electromagnetic spectrum. There are a couple of different models that have been proposed for the expansion of the universe. These have been proposed over many, many years. So here are 4 of those models laid out in a nice graphic. we look at this arrow here, the past is down at the bottom of the vertical axis. The future is at the top of this vertical axis. So these first two are examples of what we call a decelerating universe model. Here we have the Big Bang. The universe expands over time, and then it starts to contract on itself in this first one. In the second one, the universe also expands, but then eventually it reaches a point where it stops expanding and it maintains its size. And then we have this second one that we call the coasting universe, where our universe begins to expand and it continues to expand at the same rate over time. And this rate is the Hubble constant, okay? And then there's another one called the accelerating universe, which says that our universe is expanding, but that rate of expansion is going to increase over time. So we're still not 100% sure about the rate at which our universe is expanding, although we can quantify the Hubble constant, and at least right now, we believe that Hubble constant to be a constant. But as we keep on taking more and more observations of our universe, we may find over time that this Hubble constant is increasing or decreasing over time. But at least at the moment, we say that we are in essentially this model here, the coasting universe, where we're expanding in size and generally maintaining that same rate of expansion over time. Here in this graph, we have a couple of universe expansion models, similar to those graphics we just saw. On the vertical axis, we have the distance between galaxies, and on the horizontal axis, we have time. So a model of our universe that begins with the Big Bang, expands, and then contracts back in on itself would be this model right here, where the mean distance between our galaxies and our universe increase, and then they start to decrease over time and everything crunches back together. In yellow is the model where we have a constant expansion of our universe, and we can draw a straight line there. And in red is an example of a universe that is not just expanding at a constant rate, but expanding at an accelerating rate. So over time, the distance between galaxies gets larger and larger. There are a lot of questions that I saw in your discussions that were really great questions that I just wanted to highlight again here. And you would have found the answers to those in that Crash Course Astronomy video about cosmology that I asked you to watch. But let's highlight some of these big important questions that I think are really important to be sure we understand. What is the universe expanding into? If our universe is expanding, what is it expanding into? Well, that question is really not a question that we want to ask, because the universe does not expand into anything. It is the universe itself that is expanding. It doesn't really make sense to think about what is it expanding into, because the universe does not require space to exist outside of it. The universe is a thing, and that thing is just expanding. We're not going to put a boundary on it and say that there's a difference between stuff outside and inside. No, the universe doesn't need for there to be anything to exist outside of it. Imagine our universe as a sphere, and that sphere just keeps on stretching and stretching and stretching and stretching over time. It doesn't matter what's going on outside of it. We don't even ask that question in cosmology. So here we come to a really important point, and that's that the expansion of our universe is actually an expansion where the metric, the scale of the universe, changes itself. So it's more like, and in the Crash Course Astronomy video, they talked about you have a ruler. Imagine you have a meter stick, and you've got all the marks on the meter stick, and I'm going to stretch that meter stick. Okay. The meter stick might get longer, but everything I measure with it is still, if it starts at the beginning of that meter stick and ends at the end of that meter stick, everything that I measure with it, I'm still considering to be 1 meter. Even if over time that meter stick grows, I'm still saying that that full length of the meter stick is 1 meter. And so that's what we're talking about here. I know when we talk about the expansion of the universe, but you should really keep that in mind, that it's technically the expansion of the metric of the universe, the scale of the universe itself.